for spring mass damper systems for ordinary differential equations course. They can also have undamped oscillations and also something called resonance. So resonance in a mechanical system, such as a spring mass damper system, or any system that acts like a spring mass damper system, is when an oscillating force external to the system being applied to the system causes a greater amplitude oscillation in the system over time. So basically you're applying the same frequency oscillation to the system, and then the system just keeps vibrating in amplitude more and more over time. So the frequency causing the maximal amplitude is often called the resonant frequency, and resonance can be catastrophic, such as the Tacoma Narrows Bridge that oscillated so strongly due to just 64 km/h winds that the bridge deck just tore itself apart. And so you can look it up if you want. The video is kind of crazy how much the bridge is deflecting before it actually falls apart. So in the equation there's undamped resonance, meaning there's no friction at all. That's the kind of worst case. Real life has friction. But with no friction, the mass spring system with a forcing function matching the natural frequency will grow to infinite amplitude, at least according to the model here. So if you're undamped, then you have mz double prime, there's no gamma z prime, plus kz equals. So the natural frequency of this system will be the square root of k over m, so then the forcing function here is going to be cosine square root of k over mt. The solution to that system will have the typical C1, the homogeneous solution, C1 cosine root k over m times t plus C2 sine root k over m times t, then plus, and here it has the problem, it's t times a sine function. And so what ends up happening is even if you start out with really small oscillations, that forcing function will just kind of keep accumulating its oscillations in the system, and they'll just keep growing and growing and growing. And usually if that is happening to a mechanical system, it's going to rip itself apart. So, not good. Then the other type that can occur even when there is damping, when there's friction. So even with damping, a forcing function can still cause an oscillation that grows to a much greater amplitude than the forcing function. So the forcing function frequency that causes the maximal amplitude is called the resonant frequency of the mass spring damper system. So here we have damped resonance, so we have this real system to make it concrete. So the damping coefficient in this case is 1/8, and it's being driven by cosine of t. So the solution to this system, it's not very nice. So it ends up being the homogeneous solutions are sine of square root of 255 over 16 times t, and cosine of square root of 255 over 16 times t, and then both of those times damping e to the negative t over 16. And the square root of 255 over 16 is actually very close to 1, so it's matching very closely this value. There is a value that has a fairly complicated formula to give you the maximum deflection. But the thing to notice here is that you start out small, but eventually it grows and grows and grows, but it can't grow forever because there is damping in the system, and there's only so much energy being put in all the time from the forcing term. But the thing here is, even though the forcing term just has an amplitude of 1, 1 times cosine t, the amplitude of the system actually grows to 8 times sine of t. So it's 8 times greater than the forcing function. And so, that could be pretty bad if you have some forcing function acting on a mechanical system, and eventually it can grow to 8 times as large as the forcing function acting on the system. But that's the idea, and you probably go over this in an ordinary differential equations course. Maybe you wouldn't get too many problems on it, but they do go over it, so here it is.